So Lucius from NYU is going to tell us
Yes.
about disaggregated interventions to reduce inequality. You have 10 minutes, and we'll start now.
Great, thank you. So our paper is titled Disaggregated Interventions to Reduce Inequality, and this is joint work with Josh Loftus at LSE and Julia Stoyanovich at NYU. Here's a quick outline of the talk. I'll start by introducing our framework called the impact remediation problem. Then we'll go through some background on the different components of the framework, that's disaggregation and causal models. We'll then talk about how we can use our setup to find optimal interventions with a focus on disparity, and we'll walk through an example, and I'll close with a quick overview and discussion of areas we can build. We've been calling our problem of interest the impact remediation problem. And the goal in this problem is to find a useful formalization of existing real-world disparities that ultimately will allow us to approach them with algorithmic tools. So at a high level in our formalization, we first observe an existing disparity that we consider undesired. Then second, for now, let's assume we've come up with an intervention that might help. And third, we want to use our intervention to decrease the measured disparity. That's the high-level overview. And here's a quick toy example to make this concrete. Imagine there's gender imbalance in a job applicant pool. And the intervention we can perform, just as an example, is hosting booths at career fairs, where we only want to rebalance our applicant pool with respect to gender. We can imagine other examples as well, such as increasing access to resources like vaccines, housing, or education, but keep that job applicant example in mind. We'll return to it as we go through the talk. Our formalization here is aimed at a pretty broad range of real-world problems, so the corresponding research context is also very broad. Related areas include measurement, sociology, economic policy, causal inference, and optimization. And with such a broad range of topics, we can't cover a full list of every related paper, so here I'll just talk about the main starting points for our work. So the first paper in the list, Kuzner et al., looks at using causal models and optimization to maximize the real-world impact of interventions. And that's our main starting point that we want to build on, where instead of maximizing impact, we'll focus on disparity. Another key difference in our work is our use of disaggregation. And that's an idea discussed in this second group of papers here, which unpack concepts like race in particular, and how that interacts with causal modeling and counterfactuals. And I'll talk more about disaggregate in the next slide. I've listed a few other papers here from related lines of work, but for time's sake, I won't go into more detail on those at the moment. So for context, there's an ongoing and I would say pretty vocal debate right now within the research community about how to use social categories like race and gender in causal inference. And today I'm not going to argue for any particular view of race or social categories. There's a lot of nuance there, but I think it's important to mention to see how this discussion overlaps with impact remediation and informs the framework that we come up with. On the left here, I've drawn a causal graphical model. And that's just a pictorial representation of which variables we believe cause which other variables. So looking at this diagram, it states that our outcome is a function of some treatment as well as some social category. And if we change the value of one of the parent nodes, then the child node will change as a result. And the debate centers around whether or not we can model social categories as causal variables at all. In other words, whether or not we can draw this picture here at all, where the social category is one of the treatments. And to give you a quick sense of the types of questions discussed there, we might ask, what does a social category like race mean? Or what would it mean to intervene on or change someone's race in a mathematical model, the way we would change a treatment? And we could have a long discussion about that debate. Again, I'm not advocating for any particular view there, but what I want you to take away today is just that whatever we choose to do mathematically with social categories, our modeling decisions will end up translating to sociological assumptions. So the approach we've taken in impact remediation is to relax our required modeling assumptions to the point where we're able to avoid many of the difficulties of thinking about social categories as treatments. For impact remediation, we measure a disparity across groups of people, and that can be racial categories, genders, disabilities, or really any criteria, social category or not. And we do still need to think deeply about how we're categorizing because we won't see what we don't measure. But now we don't have to worry about social categories as treatments. We have our corresponding graphical model on the bottom here, where instead of having the social category as one of the treatments, we've now disaggregated our outcome across the different groups of interest. And here I've just written arbitrary groups A and B as an example. So with that understanding of disaggregation, I want to talk about the rest of the framework we've set up for this impact remediation problem. Essentially, what are the ingredients? We have n individuals Returning to our example from before, say 425 potential job applicants. We have M subpopulations on which we can intervene, say 2 universities. I'll also refer to these as intervention sets or sets of people for which we can intervene. We have R subpopulations across which we see a disparity. Let's consider binary gender for now, with female as group A and male as group B, and our outcome of interest Y that's disaggregated. Y could be the fraction of students who applied for the job. We have real world features X. Let's say X is the number of career counselors at each university. And this could be any number of features. We'll just think about one for now. And last, we have our possible intervention E, whether or not we hosted a booth at the career fair. So for today's talk, I'm going to restrict the causal model we consider to be one that looks like the graph on the right here, where X and Z have no unobserved confounding or causal relationship between them, and they both affect our outcome Y for each group. We'll also allow for interference here, where the outcomes Y for one unit, one university, depend on the treatment of both units, both Z1 and Z2. So say, for example, these 2 universities partner and they allow their students to attend either career fair. Notice we have a multi-level nested structure here where we care about these N individuals, the 425 applicants across gender, but our intervention occurs at a group level over the M intervention sets, the 2 universities. Now that we have some notation describing our framework, how would we actually use our setup to rebalance that applicant pool with respect to gender? To quickly demonstrate what that might look like, I've added some example numbers and equations here to walk through. So up top, we have counts for students in each gender group at each university, adding up to our 425 total students. And imagine we've observed the following application rates in the second line there for each group at each university, where group B has higher application rates at both locations. And say, for example, we decide to define disparity as the absolute difference in overall application rates between groups A and B, notated here as delta Z. So if we have a causal model, and this is the same picture from the previous slide, then we can estimate the effects of our interventions Z on the disaggregated outcomes YA and YB. And so just for the sake of demonstration, say we get the following expected outcome rates where our interventions potentially affect each group. Then using those estimates, we can compute our disparity measure before and after intervention. And we see that with no intervention, we have delta about equal to 0.08. With intervention at University 1, even though we've improved application rates for every group, delta stays about the same. But with intervention at University 2, we're able to decrease our measure of disparity to 0.06. So for this toy example, our optimal way to rebalance these applicant pools with respect to gender is to host a career fair booth at University 2. So to recap, under the framework we just laid out, the high-level process goes like this. First, we decide how we're looking at disparities, what categories of people we may or may not consider. With those step 1 decisions made, step 2 is then to learn or assume a causal model and fit it to the data in order to estimate the effects of our interventions. Step 3, we define our objective. We decide how do we want to mitigate the observed disparity. Maybe that's closing the gap between groups like we saw in our example in the previous slide, or maybe we instead want to get everyone over a fixed threshold, and there are several options there. And then finally, step 4, we find an optimal set of interventions subject to whatever constraints we have, which could, for example, be budget constraints. So in our toy example in the previous slide, we had only 2 intervention sets, and we were able to enumerate all possible interventions. But in a larger decision problem, with more intervention sets or more complicated constraints, that step can be done with a mixed integer linear program, for example. So that's the overview. And we can see that there are many research areas that our framework connects to. So we can think of somewhat distinct modules here of modeling treatment functions, optimal policy learning, and then bringing those together to tackle existing inequality problems with our disaggregated approach. And in the paper, we're able to talk a bit more about how this framework connects to these research areas. I would also encourage you to have a look at the paper for a more comprehensive and realistic demonstration of impact remediation beyond the toy example we saw here. And these are some of the figures from that example. So feel free to check out the paper for details. Here are some references. And that's all I have. Thank you.